Let's start with a wild thought. Everything you see, hear, taste, and touch, it's not the real world. Not really. It's actually a translation, an interpretation that's happening inside your body, second by second. And today, we're going to pull back the curtain on exactly how that incredible process works.
I mean, really think about it for a second. How does the simple physical pressure of your finger on a screen become the feeling of scrolling? How do waves of light become the experience of seeing a sunset? It feels almost like magic, doesn't it? But it's not. It's biology. And we're about to follow the clues and crack the code.
So to figure this out, we're going to go on a little journey. We're going to follow a single sensory signal, let's call it our messenger, from the very beginning, from the outside world, and track it all the way to its final stop inside your brain. And by understanding this one messenger's trip, you'll pretty much understand how all of your senses do their thing.
All right, so every journey has to start somewhere. And for our messenger, it all begins with a spark, a stimulus. Just imagine you're wrapping your hands around a warm cup of coffee. That feeling of pressure, the feeling of heat, that right there, that's our stimulus. It's the physical event that kicks this whole amazing process off.
And this initial step, this process of just gathering up all that raw data from the world, well, that has a name. It's called sensation. It is the first absolutely crucial step. Your body is basically a data collection machine, constantly pulling in information about light, sound, temperature, and pressure from all around you.
Okay, so the world provides the stimulus. But what in your body actually catches it? That brings us to the first official stop on our messenger's journey, where we meet the gatekeepers of your nervous system. These are the sensory receptors.
So what's a sensory receptor? It's a tiny, highly specialized cell that has one job and one job only, to detect one specific kind of stimulus. You've got receptors in your eyes built just for light, different ones in your skin for pressure, and others in your nose just for chemicals. They're the frontline workers, the first point of contact for everything you experience.
Now, what's really cool is this idea of a receptive field. Think of it like a receptor's personal space. For a touch receptor, that space is basically zero. Something has to physically make contact. But for hearing, the receptive field can be the size of a room. And for your vision? Well, get this. The receptive field can be light years wide. It's how you're able to see a star that's trillions of miles away. It's incredible.
And all of this specialization, it isn't random. It's all been carefully shaped by evolution. As this quote points out, what an animal needs to sense to survive is what shapes the kind of receptors it develops. And that leads to some absolutely wild abilities out there in the animal kingdom.
I mean, just take sharks, for instance. In the deep, dark ocean, seeing isn't always the best option. So they evolved special receptors that can detect the tiny electrical fields that other animals give off just by moving their muscles. They are literally sensing electricity to find their prey. It's a real-life superpower born out of necessity.
Okay, so our messenger, the stimulus, has been detected by a gatekeeper, the receptor. Now we get to the most important, the most critical moment of the entire journey. This is the magic moment where the physical world gets translated into the language of the brain. And that language is electricity.
This whole translation process has a pretty cool name. It's called sensory transduction. And I'm not kidding, this is the foundation of every single thing you feel, see, and hear. Without transduction, that warm coffee cup is just meaningless pressure. Sunlight is just radiation. Transduction is what turns all of that raw data into information your brain can actually use.
So how does this translation actually happen? Well, first, the stimulus, like the pressure from the coffee cup, physically bends the outer layer of the receptor cell. This bending forces these tiny little gates, they're called ion channels, to pop open. When they open, charged particles rush into the cell, which changes its electrical voltage. And if that electrical change is big enough, if it crosses a certain threshold, bam! An electrical signal, called an action potential, is fired off like a starting.
Now there's a really important distinction to make here. You've actually got two types of signals. The first one is the receptor potential. It's graded, which means a gentle touch creates a small electrical change, while a harder poke creates a bigger one. It's kind of like the initial push you give a domino. But the second signal, the action potential, that's the big one. It's all or nothing. If that initial push is strong enough, the nerve fires at full strength every single time. It's the domino that falls and starts the whole chain reaction.
So our messenger is now officially an electrical signal, an action potential, and it's racing towards the brain. But here's the thing. It's not just a simple on-off switch. No. This signal is actually a sophisticated piece of code, and it's carrying a ton of detailed information about that original stimulus.
So what's packed inside this secret code?
Well, it's basically 4 key pieces of information. The type of feeling is coded by which nerve pathway it travels on. The location is coded by exactly which receptor on your skin got triggered. The duration is simple. It's just how long the signals keep firing. But what about intensity? How does your brain know the difference between a light tap and a hard shove?
Well, this is one of the brilliant ways it does it. It all comes down to frequency. A gentle touch might make a nerve fire, say, a few times a second. But a really hard poke? That causes the same nerve to fire way, way faster, maybe hundreds of times a second. Your brain reads that higher frequency and interprets it as higher intensity. Simple, but so effective.
And there's another trick, too. A stronger stimulus doesn't just make one receptor fire faster. It's also big enough to activate a whole bunch of neighboring receptors at the same time. So the brain gets the message in 2 ways. Signals are coming in faster, and they're coming in from a wider area. It's like sending one person an urgent email versus sending a blast to the entire company. The brain gets the message loud and clear.
Okay, our messenger, loaded with all this rich information, has almost completed its incredible journey. It has traveled all the way from the skin, zipped up the spinal cord, and is now arriving at its final destination, the complex processing centers of the brain. And this arrival isn't chaotic at all. The brain is unbelievably organized. It's like a massive city with a perfect highway system. Signals from your eyes travel on a dedicated vision highway straight to the visual cortex at the back of your brain. Signals from your ears take the auditory highway to a different spot. Every single sense has its own private pathway and its own specialized destination. And this right here, this might be the most mind-bending part of this whole story. You see, all these signals from sight, sound, touch, they are all fundamentally the same thing. They're just sparks of electricity. The only thing that makes them different is where they end up in the brain. Just like the quote says, if a signal lands in the auditory cortex, your brain interprets it as sound. Period. The experience is created by the destination, not the messenger. So let's bring this all together. After following our messenger on its amazing journey, what's the big takeaway? It's this. Your senses, your eyes, your ears, your skin, they aren't clear windows looking out into the world. They're more like data collectors. They're translators. Their job is to take the raw physical stuff of the universe and convert it into an electrical code that your brain, the master interpreter, can then decode to build your reality from scratch. Which, of course, leaves us with one final, pretty deep question to think about. If everything we experience, every color, every sound, every feeling, is just a translation created by our brain, what is the world actually like in its original, untranslated language? What is reality before our senses get a hold of it? Now that is something to chew on.